Loop equations part 1, batteries and capacitors. We're going to run into loop equations with resistors later, but this is our first run at what a loop equation is, and we're going to employ batteries and capacitors. Kirchhoff's loop rule is a rule used for writing equations that relate to electric circuits. The basic steps for writing such equations are as follows. Start at some point, any point, on the circuit's pathway. Travel around the circuit, either clockwise or counterclockwise, eventually returning to the starting point. As we go around the circuit, we increase or decrease the voltage as appropriate whenever we encounter a circuit element. By the time we have returned to the starting point, the amount by which we have increased the voltage and the amount by which we have decreased the voltage will exactly cancel each other, leaving us with a net change in voltage of 0. So once you get back to your starting point, you end your equation by writing equals 0. Here are the guidelines for the circuit elements, batteries, and capacitors. As we pass through a battery, if we're traveling in the direction of its negative to its positive terminal, the voltage increases by plus V. If we're going from its positive to its negative terminal, the voltage drops by negative V. Here's a battery symbol. That's the positive terminal, that's the negative terminal. And we said we need to go around the circuit. We might go through the battery in this direction as we go around our loop. If we do, then we need to write plus V in our equation. On the other hand, there's our battery, and depending on what way we choose, we might be going around the circuit in this direction, which is fine. If you do, you have to write minus V when you go through that battery. That's what we're saying in statement 1. Point 2, as we pass through a capacitor in the direction of its electric field, the voltage drops by opposite Q over C. If you pass through the capacitor going opposite the electric field, then the voltage increases. When you have a capacitor here, and you've got, let's say, positive charge on that plate, negative charge on that plate, the electric field goes like that. If we're going in the direction of the electric field, you got to write that in your equation. On the other hand, here's your capacitor. It's charged up. The electric field points away from the positive and toward the negative. If we're traveling around our circuit and we go through the capacitor that way, then it's plus Q over C. Here we're going to have battery, and what's going to happen is we're going to get some charge that accumulates equal and opposite charges on each plate. There's our capacitor right there. And we've got charge flowing that way. Now, we drew this as a nearly continuous arrow. It's nearly continuous because the current can't flow through the insulator. It can't flow through the dielectric. When we're charging a capacitor, no charge flows through the capacitor. So that's why we didn't complete this circle. It only goes part way around like that. Now, figure 2 shows when the capacitor is fully charged. When the capacitor is fully charged, there's our positive terminal, there's our negative. The capacitor is now charged up. There's an electric field between the plates. I'll signify that with an E. We've got a charge on the plates. There's the capacitor. No more current flowing, so we don't draw any more arrows. So that's what we have when we have a charged capacitor. When the capacitor is charging, then we've got some current going around in that direction, but not a continuous loop. Let's write some loop equations. We're going to start at point A, and we're going to end at point A, and we're going to go clockwise. So here we go. We're going to travel through the battery in that direction. That means we write plus V. I'll put a plus there to accentuate that. We continue around. We go through the capacitor in the same direction as the electric field. So we write minus Q over C. and then we're back to point A, so we write equals 0. Now these loop equations, we're not talking about current going around. We're just walking around the circuit, making one complete loop. The current is something different. So now, what if we start at point A, but now we go counterclockwise? If we did that, watch my pen, the first thing we would run into is the capacitor, and we would be going opposite the electric field, so we would write plus Q over C. Now we keep going, all right, we're not done yet. Then we go through the battery in that direction. That means we write minus V, and now we're back to point A, so you write equals 0. What if you started at point B and went clockwise? You start at point B and you went clockwise. Watch my pen. The first thing we would run into is the capacitor in the direction of the electric field. So the first thing you would write would be minus Q over C. Now let's keep going. We're going through the battery in that direction, so we write plus V, and now we're back to our starting point, so you write 0. And finally, if you start at point B and you go counterclockwise, what's the first thing you run into? You run into the battery going in that direction, so you have to write minus V, and then we run into the capacitor going opposite the electric field, so we write plus Q over C is equal to 0, and check it out. All 4 of those equations are exactly the same. So the point here is, when you're doing a loop equation, it doesn't matter where you start. You just start and stop at the same point. If you go clockwise, fine. If you go counterclockwise, fine. You just have to follow the rules for what the voltage does, increases or decreases, depending on what's going on with the circuit element that you run into. But it doesn't matter where you start or stop. You're going to get an equivalent loop equation in any case.